5g-PHOS has been a very successful project. It mainly targets the deployment of novel fiber and wireless technologies converged together in order to provide high bandwidth services to a number of different applications. There have been 3 demonstrators that were targeted within the frame of the 5g-PHOS project. One has been carried out at the premises of Telecom Italia in Torino, showing actually how high data rates can be provided over fiber and then over millimeter wave antennas down to the end users in a typical passive optical network scenario. The second demonstrator is carried out at the premises of Cosmote and National Technical University of Athens in Greece, and this will show actually how you can converge multiple services over a fiber and wireless link. And the third demonstrator is the one that has been carried out here in Thessaloniki and has been mainly driven through the collaboration of the Aristotle University of Thessaloniki, of PAOK FC, PAOK Football Club, Intelligence, a Greek company in Athens, Cosmote, and NDUA.
The 5g-PHOS project is a Horizon 2020 program with a duration of 4 years. We're here today at the PAOK Stadium in Thessaloniki, Greece, to show you demonstration number 3 of the project. Demonstrator number 3 focuses on hotspot areas and scenarios.
In collaboration with the 5g-PHOS partners, we have designed, developed and implemented 2 cutting-edge technologies, namely a millimeter wave phased array antenna and an integrated silicon photonic ROADM. These 2 technologies can facilitate a configurable optical fiber wireless network that can steer the traffic, the optical and wireless resources, to where it is needed in the network. Namely, the millimeter wave phased array antenna has been installed on top of the gate for the VIP members, visitors, and the second antenna has been installed behind me at the opposite gate. Whenever the traffic is requested by the first antenna location, the millimeter wave antenna can shape 8 beams that can be steered towards the end users. And whenever the users are shifted towards the opposite antenna gate, then through fibers, the traffic is optically reconfigured to be routed at the opposite antenna location. And using these technologies, we can facilitate an up to 100 gigabit per second throughput within the network.
So, for showcase number 1, we're going to demonstrate the single user scenario, where we will show you a link of the 5g-PHOS architecture, and we're going to measure the link capacity and also test the stable performance of various services. As the first step, we're going to turn on a fiber wireless link that will provide connectivity, internet connectivity to an end user. On the client side, we're going to perform a series of tests with respect to speed, capacity and bandwidth, and we're also going to show you a 4K video streaming service in order to test and provide the proof of concept for the correct operation of the 5g-PHOS solution. After having set up the link, we are going to also cause interference into the wireless part of the link, and we will demonstrate how the 4K video streaming freezes when we set an obstacle between the 2 antennas of the 5g-PHOS solution, and when we remove this obstacle from between the antennas, the video will resume normally.
We are going to demonstrate you now the experimental setup of the third demonstration of the 5g-PHOS project. As you can see here, we have the master flexbox that generates a video stream, a data stream that is being transported through the fiber wireless link. And then when the signal is received at the slave flexbox, the video is streamed towards the slave flexbox here at that desktop PC. These two PCs are fiber connected through SFP transceivers and through the Mellanox NIC cards, and all the way from the fibers are being transmitted towards the FPGA device that is placed on top of the rack. The SFP transceivers that are transmitting the Ethernet stream from the master flexbox are being received through this fiber and fed to the FPGA. The FPGA board itself hosts a DAC and an ADC daughter board that generates and transmits the radio waveform, and this is being transmitted through these two externally modulated lasers. The radio stream itself is an OFDM waveform with 256 subcarriers transmitting a 250 megabit per second radio stream. The signals coming from the FPGA are then being amplified by two driver amplifiers and modulating the two externally modulated lasers, the two EMLs. Then the outputs of the two EMLs, the optical outputs, are being controlled by polarization controllers. They are coupled together and then transmitted through an EDFA and filtered so as to generate a 2 lambda radio over fiber waveform data stream. This multiplex signal then is being transmitted through this fiber behind the rack, and the two waveforms are then being imported at the input of the low-loss silicon nitride ROADM designed and developed by Lyonics International. The two wavelength streams then get demultiplexed and dropped at the two different ports, drop 2 and drop 4 of the ROADM device. And here we take one of the two input streams and propagate it through the fiber. The radio stream then comes through the fiber and is being optoelectronically converted through the avalanche photodetector and then amplified and fed to the millimeter wave 60 GHz horn antenna assembly. The antenna itself upconverts the signal from 1.5 GHz IF to 60 GHz for radio over fiber transmission across a 4-meter V-band link. After the wireless transmission at 60 GHz, the signal is received through this horn antenna assembly, and the signal itself is propagated to the FPGA board. Once the radio waveform is received by the FPGA board, it is being transformed again into Ethernet data stream and propagated back to the slave flexbox device.
Now I'm going to present the performance of our fiber wireless link. I will perform an hyper measurement from master flexbox to slave flexbox. And now I'm starting the hyper server on the slave flexbox. And I'll generate Ethernet traffic from master flexbox to slave flexbox. Also, here you can see the traffic in real time generated. It's an outgoing traffic from master flexbox through the fiber wireless link into the slave flexbox. And as you can see, it was able to generate 240 megabits per second.
Hello, now we have video which is transmitted from master to the slave to the fiber link, and we want to confirm it by coupling the Wi-Fi link. As you can see, I cut it with my pen, or with my body, and video stops. And video is resumed.
Showcase number 2, we're going to show the shifting of capacity that happens within the 5g-PHOS solution to place the necessary bandwidth when and where this is necessary. This happens with the assistance of the SDN framework developed within the 5g-PHOS project. For instance, we can have a scenario where the users depart from the stadium, the match has finished, the users depart from the stadium, and we would like to shift capacity from the internal area of the field to the external area of the field. Now, as users move on the outside part of the field, the SDN controller detects this shifting of capacity. The SDN controller that has been developed by our partner Intelligent is located at Athens, Greece. When the controller detects the shifting of the capacity, it instructs the master and slave flexbox units of the 5g-PHOS solution to shift the capacity to the next antenna. The next antenna gets activated while the previous one, due to lack of clients, ceases its operation. Within the videos that you're going to see next, you're going to see that when the SDN controller shifts the capacity, we have the service being stopped at the internal side of the stadium, and when the SDN controller reverts this decision, shifts the capacity from the outside, from the external area of the network of the field to the internal area of the field, the service resumes normally.
What we're going to show you here is how we use the SDN controller to change the parameters of the network. What you can see here is that we have the master flexbox, which acts as a video server, and as you can see here, this is the video that the master flexbox is transmitting, and the video is going through the fiber wireless link and reaches down to the slave flexbox, which is this you see here, and you can see that the slave flexbox is currently streaming a video file from the master flexbox here. Now, my colleague Aristotelis, who is in Athens, is going to show to you the process how we change the parameters of the network through the SDN controller, and what this is going to cause the video transmission to stop here. So, Aristotelis.
Hello from Intelligent. Here you can see on the screen the web user interface of the NPO tool, which is used to showcase the topology of the network and also to change the configuration parameters of the SDN. Currently we see that we have selected subband 10, which corresponds to VLAN tag 1. And we will be performing a change here, moving to subband 9, which corresponds to VLAN tag 2. Here we press submit, and the command is sent through the Open Daylight controller to the nodes.
And as you can see here, as soon as the command from Aristotelis has been issued in the system, the video transmission has stopped. This has happened quite soon. Now, what Aristotelis now is going to do is going to revert the change and switch back the original VLAN transmission. Aristotelis, could you please switch back?
So changing back to subband 10, which corresponds to VLAN 1, and it will resume the video.
And as you can see, the video has successfully continued its transmission. The slave flexbox has picked up connectivity again, and the video has successfully resumed.
Now, I'm also going to show you a realistic scenario for the 5g-PHOS solution deployment at the PAOK Stadium. How the 5g-PHOS solution would operate in PAOK Stadium or any other hotspot area. Now, in real life, the users arrive at the hotspot area, which in our case is the PAOK Stadium, keep coming, and as they keep coming, the SDN controller of the 5g-PHOS solution will detect the increase in the traffic load. When this increase surpasses a certain threshold, the SDN controller will automatically instruct the master flexbox unit to turn on a second wireless channel, and this channel, the second channel, will double the capacity provided at the network inside the field. As users keep on coming in the stadium, we see that also this newly added wireless channel, or subband as we call it, gets saturated. The SDN controller will again automatically increase further the capacity by adding a third wireless channel, and so on. This process will continue until all the users have entered the stadium or until the maximum capacity of the system has been reached.
PAOK participation in the 5g-PHOS research program is the evolution of the efforts having begun over a decade ago for the modernization and adoption of new technologies. Our efforts aim at the safety of the fans and the introduction of new commercial applications. Through our contact with existing technologies, we have come to experience the increasing need for introduction of innovative solutions that will meet the growing demand for better network coverage and high-speed bandwidth. Such needs especially arise in facilities accommodating a massive presence of people, such as football stadiums. In the context of this research program, PAOK FC has participated in the hotspot use case scenario, making its Touba Stadium facilities available to 5g-PHOS project, while also providing data, as well as making propositions as to commercial implementations, providing immense benefit to hotspot areas such as Touba Stadium. Our cooperation with all our partners has been excellent. We hope that the collaborative relationships developed will provide the foundation for future research projects, as well as the opportunity for direct collaborations.
We are very proud about this collaboration. This has been actually a great synergy between the academic, the industrial, and the sports world in Greece. And we were really also impressed by the professionalism of the PAOK Football Club and the great synergy that we had together. Actually, they identified really quickly that 5g-PHOS and the technologies it brings in can actually respond to the real needs of a football stadium, of a hotspot scenario, where actually fans want to have the best possible experience in connectivity. And you can imagine that there are thousands of fans typically wanting to have high bandwidth communication at the same time while being in the stadium. So this has been a very successful collaboration here, and we really look forward in taking the next steps for bringing actually these fibers and deploying them, these fibers and these antennas into the stadium and launching the roadmap towards a commercial implementation of these technologies.